Far from the clamor of our planet, a third cosmic wanderer known as 3I/Atlas hurtles toward Mars, mere days away from a close shave that ought to have every space organization on high alert. Yet, communication channels from missions have hushed, authoritative statements have evaporated, and the intruder's route carves an unusually level path across the ecliptic plane, a feat beyond typical comets. Its course is fixed, forming a narrow 5 degrees deviation from the solar system's disk, propelled by hyperbolic velocity. It navigates known space with an almost deliberate flair. So why have global observatories fallen eerily mute as 3I/Atlas speeds toward the red planet? And what if the reality proves far more astonishing and disturbing than officials are letting on? The quiet deepens with each passing hour as the rendezvous nears. The rusty, wordless world of Mars floats only 18 million miles from the incoming track of 3I/Atlas, near enough for orbiting probes to capture every nuance, assuming anyone's paying attention. However, updates from Mars Express and the Trace Gas orbiters stay mostly empty. No media releases, no progress reports. The live data feeds, typically buzzing with images of swirling Martian winds or icy seasonal caps, now stick to standard experiments. Nothing about the extraterrestrial guest slicing through their airspace. Behind closed doors in control centers, timelines have been adjusted. Science crews discreetly revise viewing slots, fitting in sharp focus sweeps and recalibrating tools to detect traces of water, frost, carbon compounds, and unique atomic signatures. Still, these shifts slip by unnoticed by the public. Clues emerge only in obscure operational records, hidden timestamps, minor adjustments to observation priorities, while global focus lingers on unrelated headlines. The approach phase spans just days, not longer stretches. At peak proximity, 3I/Atlas will whip by Mars at speeds exceeding 61 kilometers per second. Its glowing envelope and trailing streamer could appear dimly on any lens aimed correctly. By contrast, the previous interstellar arrival, Borisov, stayed over 150 million miles from any world. This time, an outer space interloper dips scarcely 5 degrees beyond the solar plane, forging a route that positions it perilously near Mars in a setup so straight and exact that experts in orbits dub it engineered. Nevertheless, the hush persists. No organization emerges to address the masses. The standard lineup of project experts, always eager to announce finds or flag dangers, has clammed up. Even the dedicated hobbyist groups, those tireless, gear-laden watchers who once flooded online chats like Discord and Telegram with fresh comet sightings, now scramble without fresh info. With the brush-by imminent, the sole assurance is that prime vantage points worldwide are uttering barely a word. The puzzle endures. In a realm of transparent research, what signals when the nearest eyewitnesses opt for secrecy? On July 1st, 2025, during a still evening in Chile's southern skies, the Atlas telescope array picked up a dim, swift blotch in its routine sweeps, an anomaly mismatched to any cataloged path in our system. Alerts zipped to trajectory specialists around the world within hours. Come morning, the Minor Planet Center had cataloged initial position measurements, sparking a hunt for prior sightings. In the Zwicky Transient Facility's vast image vaults, a few shots from June 14th revealed the identical blur, lurking undetected for weeks prior to formal spotting. As more observations piled up, the orbital model sharpened, revealing a narrative beyond question. This intruder hailed from the void. The path calculation solidified swiftly. Eccentricity surpassing unity. Incoming hyperbolic surplus speed pegged at 58 kilometers per second. The tilt, barely below 5 degrees to the ecliptic, drew immediate notice. Typical deep space intruders slice at sharp inclines through the system, yet 3I/Atlas diverged sharply. Its route clung to the planetary alignment, a channel so even that forecasts placed it threading the core zones with eerie accuracy. Mars, Earth, Venus, and Jupiter all fell inside a tight swath of potential encounters, resembling a deliberate itinerary sketched by navigators. To those studying celestial mechanics, this wasn't merely uncommon, it bordered on unheard of. Computer models of countless hypothetical interstellar paths yielded just a few with such aligned, multi-world alignments. The Atlas Group's veteran skyscanners passed their findings to path simulators and probability experts. They executed vast Monte Carlo runs, tracing the orbit across eons in both directions. Conclusions were ironclad. No earlier ties to the Sun's domain, no feasible Oort cloud routes. 3I/Atlas had arrived from interstellar realms, untethered to our star, on a one-way vector. The slim chance of this route-like alignment, under 1 in 500 among documented interstellar types, bolstered all further analyses. To researchers, the implications rang loud. A confirmed outsider, backed by historical and current observations, was set to traverse the solar system's vital core. Its low-inclination hyperbolic trajectory laid the groundwork for the ensuing discoveries. A near encounter with Mars, followed by multiple planetary flybys, built an increasing awareness that this wasn't your typical comet. The observations were clear, yet the inquiries were just starting. Positioned at 6. For astronomical units from the Sun, well past the frost line, 3 bright, icy outbursts occurred. That initial surge in luminosity, detected by photometry groups in the southern hemisphere, shattered conventional comet expectations. At such a range, water ice ought not to vaporize. Nevertheless, the brightness pattern climbed, dipped, and climbed once more, resembling not uniform emission but rather a pulsing rhythm. Intermittent flares, spanning from hours to days, imparted a lifelike cadence to the comet. The data spoke volumes. Hobbyists and experts, connected via Discord and overnight Slack discussions, tracked the magnitude shifting by 0.5 units, dimming, then surging anew. Typical comets don't throb in this manner. The dynamics of dust presented yet another enigma. Detailed images from observatories in Chile and South Africa displayed tail sections arcing toward the Sun, contrary to the anticipated solar wind direction. Conventional theory anticipates lightweight, swift dust particles drifting outward from the Sun, creating a standard anti-solar tail. In this instance, the tail twisted with thick clusters trailing and occasionally curving ahead. Spectroscopic data indicated a prevalence of denser, slower grains, elements that should have either sedimented rapidly or remained bound. The tail's configuration, meticulously charted by photometric specialists, resisted straightforward interpretations. While some theorized magnetic influences, others suggested explosive releases from volatile reservoirs, though no agreement emerged. When graphed across weeks, the light curve refused to even out. Rather, it stuttered. Every peak unveiled a new expulsion of vapors and particulates. Every dip implied a temporary halt or a cap over an erupting fissure. Neither solar cycles nor recognized rhythmic factors aligned with the strength or schedule of these fluctuations. The body appeared driven by inherent mechanisms, independent of outside warmth. For skywatchers, this translated to restless evenings pursuing erratic flares, adjusting gear to capture the subsequent peak. For scientists, it required re-evaluating frameworks for interstellar frost reactions and heat-induced fractures. Upon 3I/Atlas entering Jupiter's orbital path, the dust-to-gas proportions were already imbalanced. Calculations from the coma's glow implied more substance departing the core than its dimensions could reasonably support. Certain groups proposed a bigger, more volatile-laden nucleus. Others speculated on breakup processes or underground voids fueling the surplus. The sole indisputable fact was that traditional comet mechanics fell short. Coordinated photometry efforts intensified, moving from standard scans to rapid, multi-wavelength surveillance. Devices calibrated for water, CO, and organic traces operated nonstop. Watchers documented each luminosity spike and tail irregularity, reinforcing the conviction that 3I/Atlas transcended mere frozen drifters. From the outset, its unconventional actions called for innovative instruments, fresh perspectives, and a commitment to pursuing evidence unswervingly. Every prominent observatory able to view 3I/Atlas remains vigilant, even if admissions are rare. At the European Space Operations Center, operators of Mars Express have discreetly integrated updated targeting into the agenda. Orbiter spectrometers, set for methane and H2O detection, have been subtly aimed at the comet's envelope to probe for complex compounds and uncommon isotopes. Such modifications appear in operational logs, not media announcements. The tweaks are understated, an additional sweep in one spot, an adjusted time frame elsewhere, but they accumulate into a swift, confidential initiative. Across the system, the James Webb Space Telescope has reserved key slots amid its packed itinerary. During the March-September window, an expedited request activated JWST's near-infrared spectrometer and MIRI for detecting traces of untouched chemicals, hydrocarbons, mineral silicates, and carbon monoxide, intact from the comet's interstellar voyage. Internal evaluations, glimpsed in abstracts, label the scenario a singular chance. However, the approved time includes a caveat. The solar interference period approaches, and not even JWST's SHIELD can maneuver to observe during alignment with the Sun. Hubble's team has greenlit a sequence of frequent imaging sessions targeting the luminous shroud of debris and gases around the nucleus. Preliminary findings pose a conundrum. The quantity of expelled matter, deduced from the coma's intensity, vastly surpasses projections based on the nucleus's apparent scale. With the core measuring under 6 kilometers in diameter per imaging data, the emission pace demands factors beyond mere solar influence. Various analysts advocate for concealed depots or ongoing disintegration. Others recommend restraint, citing the uncertainties inherent in distant comet studies. Beyond the O through unofficial pathways, a worldwide cadre of hobbyist stargazers has emerged as the essential pillar for ongoing surveillance. Teams in locations like South Africa, Chile, and Australia synchronize their efforts to beat the dawn, documenting every flare-up. Platforms such as Discord and Telegram buzz with unprocessed light measurements, quick spectral captures, and log spikes in brightness. Debates ignite over techniques for calibration and gear availability, yet the influx of information persists unabated. Should the comet's envelope dim or its tail twist unexpectedly, these enthusiasts typically detect the shift first, often well ahead of official notifications from experts. With the eclipse period drawing near, no sighting is insignificant. Soon, satellites circling Mars will serve as the sole clear observers. Iconic instruments like Hubble and the James Webb Space Telescope must pause operations, bound by their solar exclusion guidelines that bar them from the spectacle. During this short interval, the mission's success depends on a few orbiting probes and the determination of a dispersed group of observers, all scanning for indications that this cosmic wanderer exceeds the status of a typical comet. Time presses on, transforming the incoming reports into a vital conduit. In the lead-up to closest solar approach, the authorized hush intensifies. Preliminary papers taper off. Workshop panels shut down. Documents that were once standard now bear labels such as security protocols in effect or restricted to internal eyes. Researchers who previously swapped casual notes on Slack about lens selections now communicate via veiled terms or fall silent entirely. A few unauthorized disclosures emerge. Fragments from operational discussions, a censored thread of emails headed, "Hold all data pending updates." The customary flood of unedited visuals from Mars Express diminishes to a drip. The records are there, but entry is barred, at times for several days. Within these hushed spaces, irritation builds. Avi and his allies championing mid-course intercepts press for an impromptu orbital detour. A retooled Juno might swing by. The reply arrives promptly, impractical. Funding constraints are referenced. Threats to core objectives are highlighted. In a chat thread on Slack, a lead coordinator states, "No way. Objectives locked in, no fuel for maneuvers." The idea fizzles in oversight groups, bypassing any broader conversation. At the same time, murmurs circulate among volunteer circles. A pilfered message alludes to an engineering glitch, though specifics get erased prior to broader dissemination. For each speculation, a rebuttal follows. Information is stockpiled for unified unveiling or withheld to prevent errors in analysis. The observation blackout looms, carrying the fear that prime findings might stay concealed. Currently, the corridors of space research fall eerily still. Unsettlingly so. Late September 2025. The timer to perihelion ticks forward. Yet for observers on Earth, visibility is on the verge of disappearing. As 3i/Atlas draws nearer the Sun, its angular distance from our star shrinks under 15 degrees, vanishing into the sun's fierce glow. Hubble and the James Webb Space Telescope, adhering to rigid sun avoidance policies, shift into mandatory standby. Their activity records, lately brimming with timed logs and pressing adjustment memos, now sit empty. Over almost 2 weeks, spanning October 29th to November 10th, the planet's premier observatories lose sight of the extraterrestrial comet during its peak vigor. Mars, lagging only 18 million miles away, emerges as the isolated outpost offering unobstructed perspective. Mars Express and the Trace Gas Orbiter, not originally equipped for comet pursuits, managed to fit in any feasible scans from their sensors. Their operators, laboring amid official reticence, adjust analyzers, redirect cameras, and transmit data bursts via the narrowing gap before solar noise jam signals. Each bit of information matters immensely. The campaign's trajectory now relies on the durability of these satellites and the resourcefulness of their crews. On the outskirts of solar radiance, meanwhile, the SOHO and Stereo missions hold position. Their sun-shielding devices, crafted to obscure the star's direct rays and expose subtle streams of charged particles, could snag a view of 3I/Atlas grazing their viewfinders. However, these represent sidelong gazes attuned to luminosity, not the chemical signatures or particle speeds that fueled initial efforts. The once vast flow of inputs contracts to a sparse stream. The shutdown is absolute. For the initial occasion since its detection, the narrative of 3I/Atlas unfolds out of range from terrestrial tools, leaving humanity in suspense for the subsequent developments. October 31st, 2025. Perihelion. For months, arguments have revolved around one persistent query. Precisely how large is the nucleus of 3I/Atlas? Initial views from Hubble and JWST limited the core to less than 6 kilometers, but as the object approached Mars, estimates rose steadily. Certain imaging analyses, propelled by the enormous volume of particles ejected from the envelope, now suggest a central body spanning up to 10 kilometers. Should that hold, it ranks as a giant among spacefarers, with consequences echoing across all projected paths. Simulation experts hurry to outline the endgame. 3 primary possibilities lead the talks. The disintegration would disperse to fragments skimming the orbital path, every piece offering a glimpse into the comet's concealed makeup. A striking burst, a sudden eruption of vapor and debris, might indicate disintegration or a core loaded with volatiles unleashing its mysteries through one fierce outburst. Yet enduring the encounter would pose the most piercing inquiries. Should 3I/Atlas navigate perihelion unscathed along its shallow angle, skim-like route without disruption, scientists would need to account for not only its resilience, but also its purpose, whether organic or designed. Conventional researchers favor the idea of an interstellar wanderer brimming with unstable compounds, attributing its peculiarities to concealed frosts and alien compositions. Still, a persistent faction sustains the artificial probe theory, citing the aligned flight path and intermittent emissions. At present, the core stays veiled amid brightness and conjecture. The climax lingers amid the sun's blaze. Even under rigorous examination, crucial puzzles persist. The origin of its periodic behavior, the composition of its heavy particulate clouds, and the reasons its bulk and envelope dimensions stray from conventional frameworks. With terrestrial monitoring halted during solar alignment, solely Martian satellites and sun-watching instruments provided sporadic oversight. The findings underscore a single truth. 3I/Atlas has upended traditional comet studies and revealed profound flaws in how organizations share groundbreaking information. The events at closest solar approach and the object's true essence await clarification in later records.